event having to good presentation. Okay. Just a few more details. I took my bachelor's where I come from in Greece. Then I moved to France to do my master's, where I worked on peculiar velocities. Then, as Livia said, I moved to Stockholm to also work on peculiar velocities. Now I'm also working on peculiar velocities in London, but in the meantime, I did spend some time, 2 years of my life here in Bologna, as you can see also here. So it's really nice to be back. And in the meantime, I'm also active in these collaborations. So within the Imperial consortium, I'm leading the pipeline for Bayesian inference in galaxy clustering. Within DESC, I'm leading the Bayesian pipelines topical team. And in Euclid, I'm working with Federico and Giorgio on galaxy clustering, on cluster clustering. Okay, so just a bit of motivation behind my research. Here you're seeing the number of galaxies as a function of year. In orange, you have photometric galaxy surveys. In purple, you have spectroscopic galaxy surveys. And this dashed line at the top, I took from the Hubble Extra Deep Field, from which you can extrapolate and get the number of observable galaxies in the universe. And you can see that back in the 1920s, we started from a very humble 1 galaxy, and now we're quickly reaching the limit of galaxies that we can observe in the universe with the modern observational facilities. And that means 2 things. First of all, we now have to be very careful about systematic effects because we increased our signal to noise ratio. And also, in order to optimally exploit the data that we will have available, we have to go beyond traditional methods of extracting information. Now, as you may know, typically we're using the 2-point statistics of galaxy clustering. Here I'm showing the 2-point correlation function from SDSS and the power spectrum from SDSS. And okay, this is a bit of a PDF problem, but in the power spectrum, the number of modes is proportional to the wavelength to the power of 3. And that means that we have more information at smaller scales, which we should target to extract as much information as possible. But how can we go beyond just the 2-point statistics and extract even more information? Here, I would like to show a class of methods that I worked on during my PhD and now during my postdoc, which is called field level inference. And in this slide, I will argue about why field level inference is necessary. So here on the left, you see a Gaussian field of density perturbations, let's say. And here in the middle, you see this field evolved gravitationally with some gravity model. And now here on the right, you see the corresponding power spectrum. And while here you just see random fluctuations, and here you see a very detailed view of the cosmic web, both in principle can have the same power spectrum, which means that if you limit yourself to just the power spectrum, you are doomed to misinformation from gravitational structure formation, which you can extract from higher order statistics. So how do we extract this information, or how do I extract this information in my research? I have been using this Borg algorithm, which stands for Bayesian origin reconstructions from galaxies, where we basically do the following. We start from a 3-dimensional cube of initial density perturbations. We select a gravity model, and with this gravity model, we evolve the primordial density perturbations to the present-day density field. And then, using a density likelihood, we compare the present-day density field to an input galaxy survey, and we iterate this pipeline until we get initial conditions that can predict the input galaxy survey. And the output of this pipeline is the 3-dimensional large-scale structure, both the initial one and the evolved one, as constrained by the galaxy observations that we have input. And that means that what we get in the end of this pipeline is the 3-dimensional posterior of either the density field or the velocity field within the uncertainties of the original input galaxy survey. Borg has been successfully applied to real data. You can see here an application on SDSS data. And this is a slice through the dark matter density field as a function of coordinates and distance. So the red dots that you see here are actual galaxies from SDSS. And the background color map is basically the inferred or reconstructed, if you will, dark matter density. And you can see that the galaxies nicely align with the predicted structures, with the structures that were inferred by Borg. So we can say we can have an analog of the actual large-scale structure in our computer, which we can work with. And we can take this density field and then use it to estimate peculiar velocities or the tidal shear, gravitational potential, and all sorts of different data products that we can actually cross-correlate with observations to extract cosmological information. So the question now is, what avenues can we open with this new technology that we have? In my research, I've worked on several different probes of the late-time universe. I've worked on supernovae, galaxy clustering, galaxy clusters now, and a bit of lensing. I was told that I would have 45, well, I wasn't told that I would have 45 minutes, but I was now told that I have 25 minutes. So I will talk about supernovae, and you can choose what I will talk about next. So would you prefer to listen about galaxy clustering or systematics of weak lensing? Any specific preference? Because I have to make a choice. No specific preference. Okay, that's fine. Okay, so I will start with my most recent work on supernovae in the large-scale structure. And it is indeed an exciting time to pose new questions, because we will have an immense increase in the number of supernovae that we will have available. Here again, you see the number of supernovae as a function of redshift. And especially in the low redshift universe, we will get a 5 times boost in the number of supernovae that we will have. And that means that we can pose questions that we couldn't pose before. One of them is how we can use our knowledge of the large-scale structure, which I showed in the previous slides, to understand the effect of the cosmic environment on supernova observations. And the second one is how can we utilize supernova data optimally through cross-correlations with the large-scale structure. And when I was thinking about supernovae, I immediately became interested in the Hubble tension, of course. Just as a recap of how traditional analyses of H0 are being done with supernovae, this is the 3-rung distance ladder that the SCHUSS collaboration has been using. In the lower rung, we're using very nearby objects to constrain the period luminosity relationship. In the second rung, we're transferring this calibration to the supernova magnitudes. And finally, in the last rung, we're using those magnitudes to predict, to infer the Hubble constant, where the impact of peculiar velocities is the smallest, beyond redshift 0.023. Okay, and with this 3-rung distance ladder, the Hubble tension persists. So these are measurements of the Hubble constant as a function of publication year. And dare I say that it even becomes worse. There have been several proposed solutions. The first one is some sort of unknown physics, some early form of weird dark energy. But there's also a lot of work invested into probing the systematic effects that can explain the Hubble tension. And among those systematic effects, immediately what we can look into with Borg is the effect of peculiar velocities. So how do we infer H0 from supernovae? We're typically using distance moduli and observed redshifts. But both those observations are affected by peculiar velocities due to redshift space distortions. And in particular, if you look at the Hubble diagram here, the combined effect of peculiar velocity is to shift a data point, both in the X and the Y axis. And as I said, traditional analysis impose a lower limit on the redshift to get rid of peculiar velocities. But in fact, now that we have knowledge of peculiar velocities in the nearby universe with Borg, can we use them to actually exploit this range of lower redshifts that we have been discarding so far? And the answer is yes, that we can forward model those observations with Bayesian hierarchical modeling and use them to infer the Hubble constant. So this is the current landscape of what people have been doing, because clearly we're not the first ones to have thought about it. Most people use random n-body simulations, so without any external input for how the actual universe looks like, or data-constrained reconstructions, but using linear theory. If you recall, Borg actually has a gravity model implemented, so it can go beyond linear theory. So with Borg, we can account for the specific realization of our universe and also model the nonlinear dynamics. So this is the additional advancement that I will be talking about here. I think I will not have enough time, so I will skip why modeling matters. You just have to take my word for it. And the next step is to basically build a hierarchical Bayesian framework for the inference of the Hubble constant. Ideally, you want to marginalize over the unknown cosmological redshifts and the unknown peculiar velocities. And under some assumptions, it turns out that you can come up with this pretty simple expression for the posterior of H naught using the Borg peculiar velocities. Now, what do we do with this? We first have to create type 1a supernova mocks to validate this model. And this is one of the things that I did in this paper. So I started from, well, actually, those people did it. They started from the initial conditions as constrained by Borg, and then they ran an n-body simulation. And what came out is a very detailed reconstruction of the local universe. And if you run a galaxy evolution model on top of that, a galaxy evolution recipe, which can be calibrated against actual observations in the universe, you get this very nice simulated galaxy catalog that emulates the large-scale clustering of galaxies in the real universe. So this is the simulation, this is the real universe. Therefore, what does that tell us? That we can use those emulated galaxies and treat them as potential supernova hosts to create a realistic mock. So this is exactly what I did. I used the star formation histories of those emulated galaxies. I predicted supernova rates and then sampled events assuming Poisson distribution in the large-scale structure. And what came out was a simulated data set. Here you're looking at around the Coma cluster. The white galaxies are actual galaxies in the universe. The purple galaxies are simulated galaxies, and the orange stars are type 1a supernovae, which we can now use to infer the Hubble constant. This is a bit of a detail, but the host properties reproduce the actual observations in the universe, and I'm talking about the scalings of the star formation rates as a function of stellar mass and so on. And this is our mock Hubble diagram, where I basically went from the original data to some mock observations by adding the effect of redshift space distortions and observational noise. Okay, and now with that at hand, we can actually start posing questions. So the first question is, what is the effect of peculiar velocities on the inference of H naught now that we have this very advanced modeling of peculiar velocities? So I can generate mock data affected by peculiar velocities and wrongly ignore them in my analysis. And this is what we get. So indeed, we get a positive shift. So it could explain part of the Hubble tension, but the truth is that it cannot explain all of it. So it's about 0.5 kilometers per second per megaparsec that we can account for, assuming that we have completely ignored the modeling of peculiar velocities. You can sort of look at what direction you're getting this contribution from. And there is a mild preference towards the Hydra Centaurus cluster, but nothing too significant. Yeah, I have to be fast. And then the final question that you can pose is the following. Can you misspecify, can you make a wrong assumption about H naught and expect this model to correct it? And the answer is yes. So here I created 9 different mocks, which they differ in where they locate the type 1a supernovae in the universe. And I expect my model to correct for peculiar velocities and recover a plausible value of H naught. And indeed, we are centered, all of our posteriors are consistent with the ground truth, which you see here with the dashed line. So yes, any questions so far? Because this is the end of the first paper, the end of our most recent work.
How unique is the solution that you found? Or it's finding so where you recover everything. So it's unique solution would have any possible solution for the same problem.
Are you asking?
The bit of it only evolution,
Mm-hmm.
so which is mixing phases and whatever. So I wonder if that's the solution that the condition to the initial final state is unique or not. It's not.
So the relationship between initial conditions and the final density field is deterministic because it's determined by the gravity model. There's no random dispersion in there.
There are other issues
Yes.
that are giving the same final solution.
Within uncertainties.
Yes.
Yes. So what we start from is a posterior of three-dimensional initial conditions, all of which are plausible solutions to the problem. And by marginalizing, maybe I didn't mention that explicitly, but I'm marginalizing over all plausible velocity fields. So I am actually taking into account this variability. I see 4 messages on this.
Yeah,
maybe these
so-
are okay. Okay. Okay, then I can either talk about galaxy intrinsic alignment or photometric galaxy clustering. Okay, I will talk about galaxy intrinsic alignment. Okay, so a brief summary, what is galaxy intrinsic alignment? Galaxies, elliptical galaxies that are supported by velocity dispersion tend to align their shapes with the large-scale tidal field, whereas rotationally supported galaxies, spiral galaxies, tend to align their spins. And in this paper, I was particularly interested in shape alignments, which are interesting in their own right for galaxy formation and evolution, but they're also very interesting as a systematic effect in weak lensing analysis. And why is that? Because in weak lensing, we are looking at the galaxy in a source plane, and there is a massive structure intervening between us and that source plane. The way in which we infer the intervening amount of matter is by comparing the observed shape to the original shape. But in the presence of intrinsic alignment, we cannot anymore assume a random distribution for the original shapes, but we actually have to know how the shapes of those galaxies in the source plane align with the gravitational tidal shear. And this effect, which is called galaxy intrinsic alignment, has been routinely constrained at the level of 2-point statistics, but again, with Borg, we can probe the entire information at the field level. So this is a real data application. I used 70,000 elliptical galaxy shapes from SDSS. So this is a random radio galaxy. The orange circle is the shape that you observe in the catalog. And you can predict, given the tidal tensor that you derive from Borg, what the expected shape should be. And the difference between the two is effectively the strength of intrinsic alignment. So the basic idea is that I took those shapes and I cross-correlated them in a Bayesian way with the 3D tidal fields that I got from Borg. And to do that, I had to assume this model, which is known as the linear alignment model and seems to work well on scales larger than 6 megaparsecs over h or so, and put that into a likelihood. So C here is the strength of intrinsic alignment that I'm interested in constraining. Sigma is the random noise that I'm constraining jointly, and T is the tidal tensor projected at the location of the galaxies. So these are the results. Here on the y-axis, you have the strength of intrinsic alignment, and in the x-axis, you have the scale of the tidal field. I discarded those scales that are smaller than the original resolution of the fields because we have unmodeled physics there that we don't know what to do about. And on large scales, we have the effect of the angular mask that basically dilutes our signal. However, at 20 megaparsecs, we do have a detection of the effect. A significant detection at 4 sigma, and that signal seems to be constant with luminosity, color, and redshift, but we need more data to be able to verify this statement or look for potential evolution with those properties. That being said, currently state-of-the-art constraints are being done at much smaller separations, resulting in higher significance detections. And for that, the Aquila Consortium is currently working on providing more resolved fields that we can cross-correlate our observations with to increase the significance of our findings. Should I stop?
No, please go.
About how much time do you have?
Well, at least 5 minutes.
At least 5 minutes. Okay, maybe I can say a few things about...
No, because you started 5 minutes late.
Okay, fine. Okay, Well, I shouldn't hide that one of my personal ambitions is to probe intrinsic alignment at very high redshifts, because there is potential to constrain galaxy evolution very strongly at higher redshifts. But for that, inevitably, we would need photometry, which brings me to my next paper, which is the fact that we can use the large-scale structure to impose constraints on uncertain redshift measurements. And let's see how we can do that. I will skip the introductory slide, and I will just say that when you're looking along a line of sight in the universe, and you have a galaxy with a photometric redshift measurement, you can basically use the density peaks along that line of sight to say that, oh, maybe this galaxy comes from this density peak instead of this void, because it's more likely associated with an overdensity than a void. And if we attempt to visualize this statement, the galaxy, the redshift observation would be this blue curve here, whereas the line of sight density would add this information that you see here from the density peaks. So if you multiply the two, you come up with a posterior that has additional information from the density field. Okay, and what can we do with that? So this is the original Borg pipeline, if you recall. So what I did was hack into this pipeline, and instead of just inferring the density field given the galaxy observations, I'm now inferring the uncertain galaxy redshifts given the density field, and using them to update the density inference as well. So it's like a Gibbs sampling process where both of those fields are updated. And just so you get an estimate of the dimensionality of the problem, in this particular application, I'm inferring the density field in this many voxels and the photometric redshifts of this many galaxies. So this is really a high dimensional problem that we're working with. This is a validation on self-consistent mock data that I will show, and I will jump directly to the results. These here are the mock data, so the truth. This is the density field, and this is the velocity field. And this is the mean of the inferred density field. So already visually, you can see high resemblance. And the white space here is just the survey mask. And in that space, you expect the inference to basically converge to the cosmic mean because you don't have any information from galaxy clustering. And this is the variance. So in regions where you actually have galaxies, the variance is lower because you suppress the shot noise. You can see that more clearly in the case of the velocity field, actually. Now I can attempt to quantify this statement. Before the application of the algorithm, the cross correlation of the galaxy counts with the truth as a function of scale was at most 60%, whereas after the application of this algorithm that incorporates additional information from the density field, it can be as high as 90% at the large scales. Yeah, and this is a quick slide about my work here with George and Federico. I've been attempting to improve the modeling of clustering in redshift space using different models, but this is very much work in progress, which we hope to finalize by the end of the year. And I think this is where I'll stop because I've covered my 5 minutes. And I will leave you with my outlook that we're reaching observational limits and we have to explore new methods to extract as much information as possible from the data that we have available. Yeah.
Questions, please?
How similar is your intrinsic alignment modeling approach to what is currently done in cosmic shear analysis, stage 3?
Yes.
So I think this was taken from SDSS. Hopefully it will answer your question. This is just the 2-point correlation function that is being accounted for in SDSS. Whereas in this approach, first of all, I should say that there's a difference between how intrinsic alignment is accounted for in weak lensing analysis, because this is called a direct constraint on intrinsic alignment, which means that we are not exploiting data from weak lensing. Whereas in weak lensing analysis, you want to constrain both at the same time, both weak lensing and intrinsic alignment. So there's a slight difference there. Here we're disregarding weak lensing completely. Does this answer your question?
Okay.
But the methodological difference, if I can add, is that in weak lensing analysis, typically they account for intrinsic alignment through a two-point correlation function, whereas here we're actually cross-correlating each voxel or the tidal shear projected at the location of each galaxy. So it's really the field level information that we're looking at, instead of compressing to summary statistics. Does that make sense?
Thanks.
Other questions?
Yes, so to better understand for me this method, so the input of this method are on the position of galaxies
Positions and shapes.
plus a mask. So, I mean, if you have real data and you have, you know, whatever masks.
So the mask is accounted for in the reconstruction.
So if you want to apply this to real data,
This is real data.
this is the real data. So you provide the position of galaxies and a sort of selection, some geometric selection, or a mask to say where you didn't observe galaxies.
This has already been accounted for, so maybe this is better demonstrated in that last paper that I was showing. So your survey mask would effectively be a volume that's empty.
Okay.
Of
so
galaxies,
this is
right?
so zero weight, or you would
Exactly,
have some
yeah.
weight.
Effectively, yes, because
Okay.
eventually you will marginalize over the different realizations, right? So when you marginalize, which is effectively this, you will see that there is no contribution from those regions.
Okay, so you provide this, and then it's a sort of unsupervised machine learning approach that gives directly the density, the underlying density field, and then also the primordial one, assuming in that case it's deterministic, you said.
There's a distinction. Here I'm just post-processing the fields. I'm not intervening in the actual pipeline.
Mm-hmm.
So this is just a simple cross-correlation in a Bayesian manner.
In the original method, let's suppose that you have the Euclid real catalog, the history. You can apply this method to reconstruct the current, so the density field of the Euclid observation, for instance, and then also the primordial one.
Yes. Yeah.
Okay.
With this.
So then the question, so, and it's fast, for instance, also to run on the Euclid. No.
It depends, first of all, on the resolution that you want. And one thing that I didn't explicitly say is that in order to go from the present day density field to predicted galaxy counts, you have to make an assumption on galaxy bias. So it depends also what you want to do with galaxy bias. You want to leave it unconstrained, you want to sample it jointly, and if so, what model are you going to choose? There's a lot of modeling complications that actually prevent us also from sampling cosmological parameters at the moment. So all that is for a fixed
And then
cosmology.
it's okay, so to have a description of the field without summary statistics, but if you have this reconstruction density field, and maybe you want, so you can use this method to, for instance, identify galaxy clusters of quadrant points from directly in this, and have already been tried.
Yes, I actually have some work on this, which I didn't include because it's quite old, but maybe I can show you visually what you would work with. Okay, so you can take.
Yes, and indeed also to
You can run a cosmic web classifier, for example.
also for the reconstruction, for instance, for VO, you can then if you have the velocity field, you can reconstruct the.
Yes, or even better,
But
you could actually add the BAO parameters or the Alcock-Paczynski parameters into your likelihood. Yes.
Do we have any plan we use this in Euclid, for instance, in the next data, this one?
So I'm sure there's someone within the Imperial consortium that's doing it with galaxy clustering, but that's not me.
Very quick question. Regarding automatic redshift and when you are using the cluster to constrain redshift, I mean, how much in this procedure one, or at least I take into account the point that galaxies that do not have already automatic redshift probably not share the same, say, characteristics of galaxies that for which you have already automatic redshift.
I'm not sure I understand.
I mean, if you already know the clustering, this means that for that galaxy, you already know the automatic redshift.
This is this, yes.
I mean, no, the clustering comes from galaxy. This is a question. The clustering property comes from capital the galaxy.
Yes, so in this framework, there's two things happening. So actually, there's one thing. You provide photometric redshifts, and you use those redshifts to constrain the large structure, the uncertain redshifts in the beginning. But then when you start sampling, the photometric redshifts are constrained by the large structure. So they're jointly constrained. So this is a posterior of the density field and the photometric redshift observations, the joint posterior. Now, one thing I didn't say because I didn't have time is that you can inject spectroscopic redshifts in there and facilitate this process even more. And this is what I actually did. Does this sort of answer your question? But we can discuss later if you want.
Francesco, if it's super quick, I leave you the floor for the last question.
In the first part, so on the number of observable galaxies that you presented, where do those constraints come from?
These are from the Hubble extra deep field, which is a very deep field that is not magnitude limited, to my understanding. So you can take that small patch of the sky and extrapolate.
Do you have reference?
I can.
Thanks.
Okay, if there are no other questions online, I don't think so. Let's thank the speaker again. Thank you very much.